Ladies and gentlemen, welcome to week 3. In this first video lesson, we start dealing with threshold models. Now, threshold models are just the multivariate extension of the models we have seen last week, in week 2. Those models, if you remember, belonged to the class of structural models of default, in which we have a threshold mechanism that defines the default event. Now, in threshold models, we have a portfolio of counterparties, a portfolio of exposures. Every exposure will have its own threshold, and we are interested in understanding how each counterparty may default, what happens if we consider groups of counterparties, and what happens when we start dealing with the dependence structure. That is to say, how the default of a counterparty may trigger an avalanche effect, may generate other default, may affect the possibility, the probability of default of the other counterparties in our portfolio. We will start by introducing the so-called one-period models. One period is not meant as 1 year. One period means that we define a time window between 0 and capital T, and we make our evaluations about defaults in this time window. So we might be interested in the default of our counterparties in T or within T. The point is that we are not interested in what happens after capital T. That is to say, we are not repeating our evaluations over time. And that's why we speak of one period models.
We have a portfolio with M obligors and we fix a time horizon capital T. For each counterparty, we consider a categorical variable Si indicating a state at time capital T, typically a rating. We order these quantities such that Si equal to 0 means default, while all the other values indicate better rating classes. Without loss of generality, we assume that none of our counterparties has defaulted in t equal to 0. We can then introduce a new indicator random variable yi for the event default of obligor I. Clearly, the value of yi is strictly linked to Si. Vector y is then nothing more than a vector of default indicators. With P of y, we indicate its joint distribution.
If we are interested in the marginal probabilities, that is to say, for example, I'm interested in knowing what is the probability of default of the ith counterparty, I can define the quantity pi bar, which is exactly the probability that yi is equal to 1. Now, one of the advantages of using multivariate models, of using portfolio models, is the possibility of modeling dependence, apart from the fact that they are much more realistic from a modeling point of view. When we model dependence, we can model dependence in many ways. We start with the simplest way, that is to say, by modeling the default correlation. Sometimes we also say event correlation, because for us, an event is exactly the default. We can use other ways, we can use other measures of dependence. We start with correlation. At the end of the course, in week 6, we will see that actually correlation is just a special type of dependence, it's linear dependence, and we can introduce more sophisticated way of measuring the dependence among counterparties. Okay, so let's start from the variance. What's the variance of the default indicator of the ith counterparty? So, come on. Okay, you are lazy, so just look down here, you see the expression. Now, the indicator is just taken values 0, 1. This is a Bernoulli random variable, and the variance is exactly the variance of a Bernoulli random variable, as you can see in the formula.
Correlation can be easily computed as well. The formula is on the screen. We can then define capital M to be the random variable counting the number of defaults. It is a sum of indicators, each of them is a Bernoulli. But please notice that we are not assuming the y's to be independent. The overall loss will correspond to the number of defaults times the nominal loss given default for each defaulted exposure.
For the moment, we say nothing about exposure at default and loss given default. They can be deterministic or they can be random. We will specify when we need it.
Let X be an m-dimensional random vector. X can, for example, contain the asset values of our counterparties or another quantity of interest. We can then define a set of thresholds for each counterparty and we can collect them into a matrix D. We do exactly what we did in the unit-varied case. For each counterparty I, Si is equal to j if and only if xi is larger than threshold dij and lower than equal to dij plus 1. The couple xd defines what we call a threshold model. The vector x is the critical vector, while the matrix D contains the critical thresholds. Given the system of thresholds, the marginal probability of default for our counterparty I is Fi di1, where Fi is the marginal distribution of xi. It is worth noticing that, in general, the asset correlations and the event correlations are not the same thing. They are for sure related, but they do not coincide. In particular, we can observe how the asset correlation enters into the formula of the default correlation.
Please notice that when we assume that jointly assets are normally distributed, and we can obtain these by taking into consideration a multivariate normal or a Gaussian copula, then we have that the perfect measure of dependence is correlation, because the only type of dependence we really have is linear dependence. In that case, the correlation among the assets fully determines the correlation among the events, that is to say, among the defaults. Now, for the moment, we close here. This is the first part of our introduction to threshold models. I thank you for your attention and see you in the next class. Bye!